So welcome. So the next thing we're going to talk about is inertia, mass and weight, and this is something which causes a little bit of confusion. It was Galileo 400 years ago basically who sorted out this idea of inertia, this tendency of an object to maintain its state of motion. It's like its tendency to just keep on doing what it's doing. If it's stationary, to stay stationary. If it's moving at a constant velocity in a straight line, to keep moving at that constant velocity in a straight line. And that's very much outside our everyday experience. We're used to the friction-filled world where inevitably motion stops. And Galileo was able to prove to himself and then to the world that that's because of friction, not because of any natural state of the object. And so he was able to link mass. And mass is, again, not a trivial idea. Mass is that thing that gives rise to weight in a gravitational field. It's not really the number of particles you have. It's not like, how much stuff is there. It's a very abstract thing. It's whatever it is about that substance which interacts with a gravitational field to give you weight. Frankly, we don't really have a good idea of what that is. So we get used to talking about things that are really quite sophisticated. That's fine, but he was able to kind of like deconstruct it and get to the essence of it. And the essence of it is the more mass you have, the more inertia you have. The more inertia you have, the more you tend to want to keep on doing what you're doing. The harder you have to work to change speed, or the harder you have to work to change the direction of something. And we know this intuitively. If you want to push a beach ball out of the way, it doesn't take much. You just push it. If you try to do that with a bus, it wouldn't work. It's got more mass, so it's got more resistance to being knocked around by you. So what we say is that given that F equals ma, Newton's second law, we see that mass acts to reduce the acceleration resulting from a net external force. For whatever force we have, the amount of acceleration we get depends upon the mass. In fact, what I would say is if I plot a graph of acceleration versus force, I find there's a slope, and that slope is mass. It's as abstract as that. It is the constant of proportionality. It's a quite abstract thing. If an object has more mass, it has more reluctance to accelerate. It is said to have more inertia. So a given net external force will cause less acceleration. More mass, less acceleration for a given force. And this can have interesting consequences. It's if you your motion, your behavior, we instinctively kind of estimate the mass of things when we're deciding whether to bump into them or not. If you look at a haystack or you look at a tree, you'll instinctively steer towards the haystack rather than the tree because it's got less mass, so it's easier to get it pushed out of the way. You steer towards the tree, you kind of know that it's going to be painful because there's a lot of to the extent that the tree is actually anchored to the ground, there's a tremendous amount of mass associated with that object. So we instinctively know some of these things. So more mass means more inertia, means less acceleration for a given force. Or more mass means more inertia, means more reluctance to change your state of motion. You're more reluctant to change your state of motion, whether it's moving in a straight line at a big speed or being stationary. The more reluctant you are to change your state of motion, the more mass you have. And that's none of that is kind of obvious in that language, and Galileo came along and sorted it out. All right, so we have this thing called inertia. What about weight? And again, this is a little bit confusing because we only ever live on the surface of the earth, so there's a one-to-one correspondence, well, not a one-to-one correspondence, but there's a correspondence between the amount of mass we have in an object and the amount of weight that object has. We just get used. In fact, if you look at the massing machine, this is the shame of science. If you look at the massing machine in the physics lab, which is measured in grams, which is a measure of mass, it talks about weight. And that's, in a way, shameful. It's like, what are they thinking of? No wonder we mess people up, you know. And it's just colloquial language, just sneaks in all the time. So what I need you to do is, you know, distinguish between weight and mass. Weight is a force. So weight is a force, which means it's a vector, which means it's got a magnitude and a direction. And mass is a scalar, which means it's just got magnitude. They're not the same thing. Now, yeah, in a gravitational field, I can have a force associated with a mass. But I can put that mass in interstellar space, and it has no weight associated with it. So you end up with these curious situations where if I'm, say, in interstellar space, and you say to me, can you hold that bus? I can simply go to the school bus and put my arms underneath it, and I can, you know, what am I supporting it? Not really, but I'm kind of like, it's there in my hand. So in a way, well, let's take a in a way a more relevant example, a more telling example. I can go to the moon, where there's still weight, but because the moon is smaller, there's not as much weight on any given object. So you can say to me, hey, can you pick up that box where we keep all the computer stuff? Can you pick that up on Earth? And I'll go, of course not. It weighs a couple £100, you know. I can't pick that thing up. And then we say, well, if we're on the moon, could you pick that up? And on the moon, it would have 1/6 the weight. And I go, yeah, I could pick it up, yeah. And I could. And it's much easier to pick up that object on the moon than it is on the Earth. So you might think that when you go to the moon, you become like superhuman and you can pick things up and, you know, move things around. You don't like where your space station is, pick it up and move it around, and, you know, maybe not as strong as that, but it's 1/6. But here's the irony. For those things that depend upon mass, not weight, which are things like the turnability, how easily it is to rotate something, that doesn't depend upon weight, that depends upon mass. So the rotatability is just as hard on the moon as it is on the Earth. So it's kind of like some things are much easier because there's less pull of gravity on them. So where weight is concerned, they're much easier. But where mass is concerned, they're every bit as hard as they are on Earth. So the two are not similar. They're just one-to-one correspondence on Earth, because that's all we're used to. We're not used to going to planet to planet to planet where the mass will be the same, but the weight will be different. And so we're not used to that. So we've got to practice that a little bit. So we say, well, weight is a force, and we say weight magnitude changes depending upon the gravitational field strength at the location of the mass. On Earth, the gravitational field strength is 10 newtons for every kilogram. On the moon, it's 1.6 newtons for every kilogram. So there's a huge difference. At the Earth's surface, the gravitational field strength is 10 newtons per kilogram. This means that 1 kilogram has a weight of 10 newtons on the surface of the Earth. An apple, there's something to remember, an apple weighs about 1 newton on the surface of the Earth. So you remember that old adage about the apple fell on Newton's head and he goes, oh yeah, you know, gravity, which is like, you know, maybe he did, maybe he didn't. The fact of the matter is that for us, an apple weighs about, now there's big apples and small apples, so you've got to take the average apple, you know. But it's about 1 newton from that. The moon has a gravitational field strength of about 1.6 newtons per kilogram. So on the moon's surface, 1 kilogram only weighs 1.6 newtons. The key relationship is Fg, which is the gravitational field strength. The force, which is the weight, it's the force due to gravity, is equal to the mass times this gravitational field strength. Now, this G is the 9.8 business. But I suspect you were taught it was 9.8 newtons per meter squared. Yeah? So you have been taught about acceleration due to gravity. And it's true, it's 9.8 meters per second squared. But we're talking, what I'm fearful of is you were told it was gravitational field strength or gravity. And the acceleration due to gravity is not the same as the gravitational field strength. So be specific. We're talking about 9.8 newtons per kilogram, and I prefer to call it 10 newtons per kilogram because it just makes the math so much easier. So other people disagree. And this is kind of a big deal. This is little g. This is the little g that we've learned about all along. And it's one of these things where it's little g and you kind of just get, it's no big deal, but it's a vector. It is a big deal. It's quite abstract, actually. And later on in physics 2, we're going to do that the electric field is equal to, well, we don't have mass particularly. Electric fields are all about charge. So we have Q. And then we don't have gravitational field, we have electric field. And that E depends upon the circumstances of what charge you near it, everything else. But that would be in newtons per coulomb. So what we're learning here is directly relevant to what we're going to learn next semester. So really do try and embrace this. This is gravitational field strength. It is kind of abstract. It is how many newtons for every kilogram of mass you get. And it happens to be 10 near the surface of the Earth, but it's pretty well everywhere else in the universe it's not 10. And the gravitational field is kind of like a... If I was to plot the gravitational field in this room, I would show it as a whole series of arrows going downwards, because they point downwards. That's the field. If I was to show the gravitational field strength around the world, I would show it as a whole bunch of arrows. And the arrows point in the direction that a boulder would fall. Falls towards the middle of the Earth. So we show it. And you can see, actually, these arrows are kind of quite informative. As the arrows get further and further away from each other, as the density of arrows going through a plane gets less and less, so the gravitational field strength falls off. And so later on in Physics 2, we're going to use diagrams of electric field patterns. I'm going to do math on those diagrams. We could do the math on the gravitational fields. It's just traditionally we don't do it. So this is a concept which is, it's not trivial. It's quite actually subtle, and it's really quite useful to us. The concept of the field is really quite useful. But for the moment, I'd love you to be comfortable with the fact that F equals mg, and g is 10 newtons per kilogram. I'd love it if you didn't write down meters per second squared, but you put down newtons per kilogram when you were talking about gravitational field. Okay. Let's talk about two situations, equilibrium and non-equilibrium. If I have an object and the sum of the forces acting on the object equals 0 in a given direction, so I can resolve these forces. And if the sum of the forces equals 0 in any given direction, then we are said to be in equilibrium. If the net force equals 0. If the net force does not equal 0, and I resolve these forces. So there's a net force, then the sum of the forces in any given direction does not equal 0. I'm said to be in non-equilibrium. So basically, for equilibrium, Newton's first law applies. For non-equilibrium, Newton's second law applies. We say the acceleration of an object is 0 in the equilibrium case. Object has a constant velocity. It can be 0, it could be stationary, but whatever velocity it has, it doesn't change in time. When an object is at rest or when an object is moving with a constant velocity, it is said to be in equilibrium state. So equilibrium does not mean stationary, not necessarily mean stationary. You could be stationary, but you could be traveling at 1,000 miles an hour, and it really makes no difference. Velocities are not critical. It's accelerations that we link with forces. If the net force does not equal 0, then the object will experience an acceleration in the direction of the net force. Must, really shouldn't say will, I should say must experience an acceleration. The object has a change in velocity. That means a change in speed and or a change in direction. When an object is accelerating, is it said to be in non-equilibrium state? So we divide the world up into equilibrium and non-equilibrium. I'm in equilibrium with respect to the room because I have a constant velocity of 0 with respect to the room. This divides, if you like, mechanics up into 2 bits, and we have statics and dynamics. Statics does not necessarily mean being stationary. It means not accelerating. And dynamics means having an acceleration. There's several classic situations we look at for the statics. There's the traffic light problem. So we have a mass that's suspended, and it's suspended by a couple of strings. And so we have forces of tension in these strings. They're not the same. And we have a weight, if you like, Fg down here. And the traffic light is not accelerating anywhere. It's not speeding up going to the right, or speeding up going to the left, or speeding up going vertical, or speeding up going horizontally. It's not accelerating anyway. So we say it's in equilibrium. There's another possibility which we commonly use, which is a block sitting or coasting down some kind of incline. That's another very common scenario we talk about. Why do we pick these things? Because by picking these things, they're good examples. And, you know, what happens is that everybody doing physics courses does these 2 kind of examples, so it forms a common language, a common experience, etc. They're not the only 2 things in which statics applies. Statics applies with a bridge or whatever, you know, you can go on forever. But those are 2 common examples that you'll see. And then in comparison with this, we have a thing called dynamics. And in dynamics, the sum of the forces is not equal 0. So here's a good example. We have a smooth table, and we have a mass hanging over a precipice, just pulling down, and we have a block somehow on the table. And we want to analyze that where there is acceleration. And another example of that could be where you have a mass on a slope, and now you have got acceleration. You know, and they're the kind of situations that we tend to look at. So let me get rid of this, because that's just me talking. And let's go through this. So, and the pattern is the approach is similar in all cases. Don't learn the problem, learn the approach. So here's an example. The first thing you need is a decent diagram. So do our x, do our y. This is 30 degrees, so it's going to be like that. Try not to make it 45. And this is t right. And then, well, that's 45. And this is 40 degrees, so this is t left. This is 30. This is 40. And then down here, well, I have my 3 kilogram mass, and I know that that is 30 newtons, because I know that for every kilogram I get 10 newtons of weight. So there's no need to draw the mass in, just put 30 newtons there. They come together with this little string thing here. And what I want to know is, in this case, I want to know t left. So put your teacher's hat on now. I'm a teacher. I've got to test you on this. I've got to give you questions that are solvable. And what can you tell me about a question where there are 2 unknowns? How many equations do we need to solve 2 unknowns? Yeah, 2 unknowns. You need two equations. So I'm expecting to have 2 equations to solve this. And I come along. I'm going to change my pen color because I'm kind of thinking now. And I'm going to say, well, F equals ma. It's some of the forces and the external forces and their vectors, so they're in a direction. So when I say, oh, the sum of the forces is equal to ma, there's a lot going on there. I'm saying it's external, not internal forces like we had about the car. And I'm also saying in a given direction. So there's a lot going on with this. So when I look here, whether it's sum of the forces equals ma or sum of the forces equals 0, I should think in terms of a direction. I should not use these equations haphazardly. I should have a direction in my mind. And the most obvious direction for me is horizontally. So I'm going to say the sum of the forces horizontally is equal to 0. Because I know it's in equilibrium. I know it's equal to 0 because it's not accelerating horizontally or whatever. Yeah? So then I say, oh, let's look here and visualize. What I find is when people are having trouble with components, it's often that they're not drawing the diagram. So it's almost like they kind of got their eyes closed and they're trying to fish, something out of a drawer without looking in. It's never going to be easy. But if they look in, they go, oh yeah, look, there's my original vector and I want the horizontal component. So let's draw it. So you draw it and then it falls into place. That's going to be, oh yeah, that's going to be the straight line down. So this will be t right cosine 30. And that goes in a positive direction, so I'm going to draw it like that. And then I say, well, does any other forces have a component horizontally? Well, the 30 doesn't, so we can ignore the 30. It's 90 degrees. So there's no shadow. Components are like shadows. If I have something leaning and it casts a shadow, that's like a component. If I have light coming from the side and it casts a shadow onto the wall, that's like a component. So components are like shadows. And this thing is like perpendicular. So there's no shadow because it's perpendicular to the surface. This thing casts a shadow. If the light shines down from above, we'd get a shadow. And that is my t left cosine 40. Now that's pointing in the negative direction. You can see that by my arrow. So that's negative on there. And what does it say? It says these are external forces. They're pulling on that knot. So these are external forces. So I say plus TR cosine 30 added to, because it's a summation, minus TL cosine 40 is equal to 0. So we just write out that equation. I take out my calculator. And well, okay, I'm not going to take out my calculator yet. You can work them out. You can work out your trig expressions immediately, but don't round too much. If you round too much, by the time you get the answer, you're going to be way out. So I'd give 2 to 3 decimal places if I work it out now, just because I don't want to lose out. Alternatively, you can just live with it. It's no big deal. It's just a fraction. Cosine 30 is just a number that's less than 1. It's between 0 and 1. All of these things are just numbers between 0 and 1. So you can leave them for a while if you like. One thing I do know mathematically is eventually I want to find TL, and I've learned over the years that if I want to find TL as my answer, I isolate the opposite thing in my first equation. So I'm going to say, oh, TR is equal to, take this to the other side, TL cosine 40, and now I'm going to divide by cosine 30. All I did was I took the TL cosine 40 to the other side, it became positive, and then I divided by cosine 30. Now I know because of experience that if I want to eventually find TL, isolate TR in the first equation. And if I didn't know that, and I isolated TL in the first equation, then I'd find TR in the second, and I'd have to substitute back into one of the other two equations to get TL. In the end, it works. As long as you don't make any mistakes, it'll work. But I've learned over the years that if I want to get TL by itself at the end, I want to get the other thing by itself at the beginning. It'll work out. Speaking of which, so what's next? So let's change colored pens. So let's go to a nice blue. That might show up. So now I look and I say, well, hold on, I've got that guy there. And this will be TR sine 30. It's positive because it's pointing upwards. Opposite over hypotenuse is a sine. And then I do that guy there, and that's also TL sine 40. That's also a positive. And then this is its own component. So this is 30 newtons. So now I'm only thinking vertically. And I go, the sum of the forces vert is equal to 0 because it's not accelerating vertically either. It's not accelerating horizontally. It's not accelerating vertically. So I look and I go plus TR sine 30 added to plus TL sine 40 added to minus 30, because that 30 is pointing downwards. That's a minus 30 is equal to 0. I want to find TL, so let's substitute in for TR. So I go TL cosine 40 over cosine 30. That's my very first, that's that little bit, times the sine of 30. It's just a quarter times 3/4 over a half. It's just little fractions. That's all those things are. Plus TL sine of 40. Let's take the 30 to the other side. Equals 30. And now I get my calculator out. And I'm going to go cosine 40, enter. I'm in degrees. Times sine 30, enter. Divided by cosine 30, enter. And so I get, let's look, 0.4423 TL plus Sine 40 is going to be 0.6428 TL is equal to 30. So TL, I've got to add those two guys together, don't I? Let's do that. 0.4423 added to 0.6428 is equal to, I'm going to go 1.0851 TL is equal to 30. So TL is equal to 30 over 1.0851, which equals 30 divided by second answer, and I'm getting 27.647. Choose that guy. So there we have it. Bit long. It's just doing two sums. It's just finding the components horizontally and adding them all together with appropriate signs. It's finding the components of the forces vertically, adding them together with appropriate signs, positive, negative. And then it's doing a bit of maths, you know. Basically, I got two unknowns, two equations, solve for my unknown. That's as hard as it gets, and that's as simple as it gets. If you don't have a diagram, then, you know, you struggle a bit more. If you make a mistake on your components, then, you know, you're kind of done for. It's there. It's not bad. We're going to learn other ways of doing these things. We're going to learn to get faster at them and better at them, but, you know, that's basically the layout. From a teacher's point of view, I'm being very kind here. I'm giving you both angles with respect to the horizontal. I needn't do that. I can give you the the other angle. So I could have given you the 60 up here and not the 30, and then said, okay, figure that out. It really makes no difference as long as you know how to treat the components. Basically the same thing. So that's a statics problem. And then let's do a dynamic. Well, actually, no, I'm not going to do a dynamics problem because we're going to take a break and we're going to come back. So I'm going to do a fair bit of statics and then I'll do a fair bit of dynamics. And I think that's going to make it, rather than just immediately giving you the dynamics now. But let me, before I go on, because we've got a little bit of time, so let me immediately show you how I can make my life a whole lot easier. Okay? On this same problem, if I'm clever, I can make my whole life a lot easier. So I'm going to erase this, okay? And so hopefully you've all got it, or if you've not got it, you can photograph it. I'm going to just erase that. I'm going to start again. And it takes a while. I don't think there's no lasso tool on this thing where I can just capture the whole thing. You know, I like doing things in one step if I can. And by being a bit smarter, I can do things in one step. Okay, so let's have a look at this. Let's see if I can do this in one step. You do need to be a little bit careful with your diagram. And the reason being that I don't know TL and I don't know t right. If I can ignore one of them, I can solve this thing in one step. So the way I can ignore one of them is I put my axis at 90 degrees to it. I don't want the TR, that's the one I want to ignore. So if I draw that at 30, then I draw an axis at 30 degrees to that. That's 90. That's 90. If that's 30, that's 60. If that's 60, that's 30. Agreed? So now, that's the game I'm playing. So now I draw my diagram. And here I try and make that 30. And this comes down here, and that's, sorry, 30 degrees. 30, this is bad teaching practice there. 30 degrees and 30 newtons is not good practice. And then what I do is I go and that one there is 40. And that's T left. So by using this dotted line, I can forget about that. It has no component along that line. So then I say, let's change colors. So then I say, the sum of the forces along the dotted line is equal to 0. That's the nice thing about when you're truly static in all directions. You are static in all directions. It's not accelerating up and down, it's not accelerating left and right, it's not accelerating along any line I choose to draw. So the sum of the forces in any direction equals 0. So now I resolve, this is called resolving my forces. Find the component, so the component along that dotted line is going to be TL. Now, I want to find the angle between, and if that's 40, and that's 30, that makes 70, so that's 20 degrees. So this would be TL cosine 20. You see how I did that? I recognize that there's 90 degrees in that quadrant. I have 30 degrees taken up by the dotted line, and I have 40 degrees from the horizontal by the actual force, and in between that leaves 20. So it's TL cosine 20. Then I do dot, dot, dot. And if this up here is 30, and that's a straight line, and that's a straight line, that down there is 30, bit of trig coming in. So this here is going to be 30 cosine 30. Notice in both cases I was careful to draw my components, the green arrows, and recognizing that they were shorter than the red arrows. Your components are always less long than your original vectors. That's the way components are. And now, the only thing I got to do is recognize that these are fighting each other, so one must be given a positive sign and one must be given a negative sign. I'm going to decide to make that positive. Why? Because it's Monday. I mean, you know, who cares why? It's like, it's just, you just pick. There's no real rhyme or reason. It's upwards, which would imply positive, but it's to the left, and that implies negative, and there's no right answer for this. You just got to pick. And this one is negative because it's the opposite to the positive. I have to have a positive and a negative in these. So that means that would be a positive and that would be a negative. So I come along here and I say plus TL cosine 20 added to, because it's a summation, minus 30 cosine 30 is equal to 0, because the sum of the forces equals 0. So TL is equal to 30 cosine 30 over cosine 20. So TL would equal 30 times cosine 30, enter, divided by cosine 20, enter. And I'm going to get 27.648 newtons. 27.65. There's my answer. So, looking back at those two, which do you prefer? Who prefers the first one? Who prefers the second one? In truth, as the semester goes on, you're going to need to find ways of stopping problems from blowing up and being just long. And so the smart money is on the second method. It's the more insightful way of approaching it. I understand if you stick with the first method to begin with. It's like, you don't go into a test and try new things. But I'd encourage you to master the second one. Because when we come to things like torques and the like, the whole problem is going to be where do you put your axis of turning, and that's all determined by what you want to ignore. In this case, we've been very artful. We're saying I don't want TR, therefore I'm going to pick an axis which ignores TR. That's very artful, and we'll do that over and over again. We make the math our servant, we don't just blindly follow the math. There's another way of doing this. Might as well show you the 3 ways of doing this. So copy that down or take a picture or something. I'll squeeze the other way in the corner. And the other way of doing this is actually simplicity itself. In the other way, what we do is we say the only thing we know about length is this 30 newtons, agreed? So let's just draw it as an arrow, 30 newtons long. I have no idea how long this TR vector should be. It's not the same length as the piece of string. It's an abstract arrow. It's not just how long the string is. It's an abstract arrow. I have no idea how long I should draw it, but I do know that it should be 30 degrees above the horizontal. And I have no idea how long this TL arrow should be, but I do know it approaches the beginning at 40 degrees to the horizontal. Oh, I have a vector diagram. And in a vector diagram, if it's in equilibrium, there's no resultant. The forces are balancing each other. So let's have a look. That TR must have gone in that direction because it's a TR, and your TL must have gone in that direction. And you can say, well, if that's 30, then I can tell you that that is 27 point, I don't know, 7, newtons. You can measure it. So you get your ruler and your pencil out and you just measure. That's how long it should be. We'll do a lab with that included in it. But it's got to be a vector diagram. Vector diagram's got to work. It's not as precise, but it's a vector diagram. It'll work. In fact, this is, people get to they like this last method so much that in the test sometimes they have to put down using the method of trigonometry, so they can't do a vector diagram all the time. Because it's not precise, but it's pretty good. It's within a few percent, you know, if you draw it well. So 3 methods. There's 2 trigonometric methods, and there's 1 graphical method, and the 2 trigonometric methods, you know, either or. I think the second one's kind of more insightful, but either or. And then the diagram one is really useful. Sometimes you'll find, I've had students come to me from math class with a bit of a problem that has been set in math. And I've been able to solve it really quickly using a vector diagram. And that's not allowed. You know, they're still got to be able to do it the math way, you know, using the equations. But in reality, the vector diagram is incredibly powerful. It's just not as precise. Cool. So let's take a break. So we're going to stop that.